Hello everyone. Let's talk about structural splices today. Um, Structural codes are often very heavy on text but light on visuals. We actually need to understand them. My goal is to take these dense, complex clauses and bridge the gap between, um, bridge the gap with simple hand-drawn sketches. By layering these chicken scratches directly onto the canvas of the code, we transform abstract rules into clear mental images. Many times these mental images are what are helpful in an exam setting. So this visual association makes it much easier for you to recall specific requirements when you are under pressure in an exam. In this video, we are breaking down structural splices or splice joints to see exactly how the theory translates into physical form. So let's pick up a pen and paper and turn these words into something we can actually see. Right, so I'm here. We're talking about the ACI 318, and we are talking about we are in this particular chapter, chapter 25, which is all about reinforcement detailing. In our previous video, we talked about development length of the bars. Now we are gonna talk about splices. Right. So what is a splice? It's a simple way of transferring the force in one bar. Let's say you have a bar like that. You have one bar. Here is another bar. Obviously, the bars. Let's say the bars have different ribs, right? So here is another bar, and then there is tension in this bar. Also, there is tension in this bar. So you want to translate the tension here. The whole thing is surrounded in concrete. So imagine concrete here. Imagine these are the reinforcement bars which are embedded into your beam or a slab or somewhere. So you want to transmit the tension force from this bar onto an adjacent bar. And the way to achieve this transfer is to splice them. Right. So what happens when you splice is when you try to pull these deformed protrusions that you have on the bar are going to press against the concrete, and the concrete, if you pull it real hard, then the concrete is going to crack like that, right? And same thing happens here. It's going to crack like that, right? And then eventually there might be a big crack that appears somewhere here, and when those cracks appear, then you cannot transfer this tension onto the other side anymore. So that is what a splice is all about. Let's get into the weeds. I think the information is in page 430. That's where the splice information starts. So we'll just scroll through the code, and then so as you see here, that they're talking about two different. So firstly, this is the splice section. They're talking about two different splices. There is a contact splice. There is a non-contact splice, right? And a contact splice is something like this. Let's say you have one bar here in your column. Bar cannot continue for infinity, so you want to splice it with another column. In a contact splice, you place them next to each other and then tie it with some kind of chicken wire, right? The same thing might happen for another bar. Maybe this is the other bar. It's coming down. You don't have infinite bars that are infinite length, so you need to splice them together so that the reinforcement continues from top to bottom. So this clause here is saying for a contact splice, the minimum clear spacing between the contact lap splice, meaning this is the contact lap splice, and the adjacent bar, which is this bar, or the lap splice, adjacent lap splice, shall be in accordance with the minimum reinforcement requirement. This particular section, 25.2.1 here. So if you go to 25.2.1, um, it will dictate the that minimum clear spacing, and I think it is um, there are three different values. Let's go to 25 point, or let three different values. One is 1 inch, or the diameter of the bar, or four thirds the size of your aggregate. So size of aggregate, you take the max of that, and that is the minimum clear spacing that you need to maintain in a contact splice scenario. Right? So that's about the contact splice. Like I said, splices, you have contact and non-contact. Now, this particular non-contact splice here, you have a bar here, and that bar, there is another bar slightly apart. You want to transfer this force from here. Obviously, if this spacing is too much, then you cannot transfer this force through the concrete onto the other side. So, so this particular clause here is saying, okay, if you have a splice in a flexural member, the center to center spacing of the spliced bars shall not exceed a certain value, 1/5 the required lap splice length. So when I say lap splice length, I'm referring to this overlap here, this region wherein the two bars are overlapping, that region wherein the two bars are overlapping. So that is your lap splice length. We'll give it a proper notation later on, but that is your lap splice length. So for a non-contact splice, um, you need to maintain a certain distance. Center to center distance of the splice bar shall not exceed lesser. Always pay attention on the adjective here. Lesser of these two. 1/5 the required lap length and 6 inches. So you find out 1/5 the required lap length. You find out the lap length first, and then find out 1/5 the lap length, and then compare it with 6 inch, and then take a call as to what the splice length has to be. Right. So that's the terminology here. They were to give us a simple sketch here, that would have been pretty useful. Right. So let's move on. Let's keep going. Um, Sometimes you can also reduce the splice length, and there are some rules. So we'll talk about that. And if you have bundled bars, if it's not a single bar and you have a bundle bar and you want to bundle, let's say you have bundle of 3 bars and you want to splice them with another bundle, then what is the rule? What is the minimum splice length? So all that information is provided here. Now let's talk about the most important detail. Again, the intention here is just to cover the breadth part of a PE exam or AC exam. So I'm not going to get into all the details, but all the important details that might help you to sail through the exam easily. So this is talking about splice length of deformed bars and deformed wires. We'll mainly pay attention on the deformed bars. Um, so deformed bars, how do you find out your splice length when the bars are in tension? Like the development length, the splice, you can splice a bar that is in tension, and you can also splice a bar that is in compression. The splice length in compression is usually smaller than the splice length in tension, because when two bars are getting compressed, they are bearing against the concrete. So the concrete is trying to help the bars under compression there. So they're giving it a nice notation. The notation is LST. This is not this is like this is the length. This is the splice business, and this T is referring to the tension. So LST is the notation that is being used. LST is here, and interestingly, it is dependent upon our LD value, right? So LD is the development length. We talked about it in another video. So it depends on the development length. But there is an interesting terminology here. You'll have to figure out the LST value from this table, and to enter this table, you need to, like any other table, you need to find out where you fit. Are you in this row, or are you in this row? Similarly, are you in this column here, or are you in this? I mean, or are you in this column here? And then figure out. Uh, then finally you pick up your um, splice length from this section there, right? So first let's so there are two types of splices, and there's very little information here. Uh, at least in this page, maybe it's embedded elsewhere in the code or in some explanatory guide. Um, you have a class A or a class B. So lap splice intention are classified as class A and class B, and that is the information you need before you figure out the splice length, right? Um, the length of so the lap slices in tension are classified as class A or B with length of lap a multiple of the tensile development length. Like I said, you still have to find out your development length, and you multiply it with something to finally find out your LST. This is the LST value, which is your lap splice length. So what is that multiplier? That depends upon which row and which column you end up with. Um, for example, you have a 1 times LD multiplier here, or you have a 1.3 times LD multiplier here, right? So, so to decide which one here, you need to find out if you are a class A or class B. So class A splice, before you finally find out this value here or that value here, you need to understand whether your splice is class A. You need to understand if you fit here in this row or that row, and if you fit in this column, you fit here or here or here, right? So let's talk about this one here first. So this is A, like the definition says, A area of steel provided by area of steel required. So if your area of steel provided by the area of steel required is greater than 2, you find out that ratio. If it is greater than 2, then you are within this cell, right? Now you have to decide if you still have to. I mean, the end goal is to find, should I use 1.0 LD or 1.3 LD. So you still have to figure out where you fall in this column here. So this column here is saying maximum percent of AS spliced within the required lap length. What that means is, for example, if you have a you have a square column here like that, right? I'm looking at this column. Let's say I'm looking at this column from this angle. So you have a column like that, and you have bars that are getting spliced. So let's say there is one bar that is getting spliced here, and let's say there is an adjacent bar, and that bar is getting exactly spliced at that location, right? So that means the full reinforcement, 100% of my reinforcement is getting spliced within that section, right? So these two bars are spliced within that section. These two bars are also being spliced within that section. So that means you come under that category. That means you are a class B, and your development multiplier is 1.3. If there's another scenario wherein you have your column here again, let's say I have my splice, first bar is spliced there, but the next bar is not spliced, let's say. So only 50%, or maybe the next bar is spliced, but it's spliced elsewhere. So only 50% of the bar of the area of steel is, this is one bar, this is another bar. Only 50% of the area of steel is being spliced either at this location or at that location, right? So that means you are a class you are under class A, right? So you figure out now let's talk about this a little bit further. Area of steel provided, area of steel required. What is this? So let's say you have a building, something like that, and you have your columns like that, and then let's say wind is blowing from this side, correct? When wind is blowing from that side, everything wants to lean to the right. So your let's say your bending moment diagram is something in the column is something like that in all these columns, right? I'm just trying. Nothing is to scale. The channel itself is chicken scratch, so we're just doing chicken scratches here, right? So the max moment obviously is here. Let us say this is M. So you find out the reinforcement from first principles. You find out the area of steel required. So area of steel required. You find out that. Now you provide that area of steel here, not only here, but then you continue it along the entire length. So at a section like this here, only you have the bending moment is only 50% or 40%, something like that. The bending moment is the bending moment is only that much, which is a fraction of this full moment. But the area of steel is more than what is needed to resist this 50%. So that is what that is exactly what we are trying to calculate here. What is the area of steel provided um, divided by the area of steel that is required? If that is greater than 2, and you know that you are splicing 50%, right? Then it's a class A. Then you need to find your LS. The goal is to find the LST, that is your splice length of the deformed bars. And the good news is when that happens, then you just take your LD for the bar that you are trying to splice, and then multiply it with a multiplier like what is mentioned here. And in that case, the multiplier is only 1.0. You compare that with your 12 inches, and then um, provide a splice length which is the greater of this one and that one, greater of those two. Right? And you do the same thing here. Let's say the AST by area of steel provided by the area of steel required is less than 2. Um, then either you are in this case or that case, either you fall here or you fall here based on the percentage of steel that is being spliced within the required lap length. You are a class B, and you need to take your development length, multiply it with a factor of 1.3, compare that with 12 inches, and select the greater of these two, the greater of that and that, right? So that's about this section here. Again, we just covered splice length of deformed bars in tension. Again, that sketch, here is a column, there is a bar here, there is another bar here, um, whereas so the splice is happening at this location, whereas maybe there is another bar here, maybe there is another bar here, and the splice is happening elsewhere. So only 50, but let's say this is bar 1, this is bar 2. The 50% here is about within the splice length, 50% of the reinforcement is being actually spliced. Now this fellow here is, let's say you have a column, this is the bar, that's the bar, this is another bar, and that is another bar. So within this splice length, both bar 1 and bar 2 are being spliced. That means 100% of the bars are being spliced within that splice length. So then you fall under this particular category here, and you navigate across along the table, and then you find out your LST value, right? So that's the splice length here. There's some more rules. Like I said, we are not going to talk about deformed wires. Again, there are some basic principles. So if you have a question, you know what the terminology is, what LD is, why we are trying to multiply it with 1.3, what LST is, and all that. So you can hopefully you can answer those questions. Let's keep going. Um, Now this is also welded plain wire. The other one was deformed wire. This is plain wire. Again, there are some rules, but you understand the core terminology here, so you should be in a position to calculate that, right? Now the splices, uh, they can be in you can splice you can splice reinforcement that is under compression. You can also splice reinforcement that is in tension. So what we covered till now was in tension. Now we are talking about situation wherein the bars are under compression. So maybe you have a column like that, and there is an axial load on the column, and there is also a moment, but then the moment magnitude is not significant compared to the effect of the axial force. That means all the reinforcement bars might be under pure compression. So if they're under compression, then you need to find out. I mean, how do you calculate your LSC? So instead of LST, now this is the new term, right? And this whole thing is called compression lap splice length, correct? So there's some rules regarding number 11 bars, pretty straightforward. Um, but then how do you calculate the splice length? It depends upon your Fy value. Fy is less than that, then LSC is the greater of that and that. So you compute that, you compute this, find out the greater value if your yield strength is less than 60 psi, right? And everything here is straightforward. This is diameter of the bar, that is yield strength of steel, and that just empirical constant there. Same thing here. If you find either you are here or you are here. So if you treat this as a table and you find out if you are here, then that means you are, let's say you have an 80 psi, 80 ksi steel. Then you find out 12 inches, and then compare them and pick up the greater value and report that as your LSC value, right? If your concrete is less than 3000 psi, then you have to decrease the splice length by 1/3. So that's another rule there. So when you look at a section like this, you're just not worried about one portion of it, but you will have to broaden the window till it overlaps the next section. That's when you pick up information like this. Maybe in your question, the concrete is less than 3000 psi, and you need to do this, but you also need to do that. So there are certain rules. Compression splice shall not be used for bars larger than number 12. There is a little bit of explanation on this side here if you are interested. Um, Sometimes this is another interesting section here. Sometimes you have different size bars that are being lapped. So maybe this is a number 3 or 5 or number. So let's say this is number 10, and this is number 9, and you're trying to lap two different bars. Then there is obviously you can only transfer the strength. Um, by splicing, you can, let's say the strength of the number 9 bar is X, the strength of number 10 bar is Y. You can only transfer X onto the other side. You cannot transfer, no matter how you splice, you cannot transfer Y onto this side. You can only transfer X, which is the capacity of number 9 bar, onto the other side. So there's a small rule, very clear here. Bars of different sizes are being lapped in compression. LSC shall be the greater of LDC of the larger bar, calculated, and LDC. Sorry, let me take that back. Two different sizes. When bars of different sizes are lapped in compression, LSC, the final LSC value, should be greater of LDC for the larger bar and LSC for the smaller bar. So you calculate LSC for the smaller bar. Based on all this, you calculate LDC, development length in compression, based on that particular section. We talked about it again. So you find those, and then you pick up the greater value. So that's how you deal with parts of different diameters being sliced. Um, Bars, end bearing splices are different bars in compression. Pretty simple, nothing complicated there. Now let's go to the next important section. I think that's about it. So now we are getting into 25.6 here, which is bundle reinforcement. The another important detail is hidden in I think chapter 10, which is the columns. We'll have to go to that particular page here. Um, think it is page 160. So information about the splice for a column is in a different chapter. So not everything is under that chapter. So um, let's talk about the splice reinforcement here, longitudinal reinforcement. Um, let's see what this section has to say. Right, lap splice. That's where we are. Right, this is a good diagram. I'm going to talk about it in a little while. But then, so so whenever you have bars that are being spliced, for example, this bar is being spliced with that bar, and then it is also encased in stirrups, right? So if the bars, um, whenever they're encased like that, then you can take the advantage of that confining action and then reduce the development length by either this factor or that factor. So which is the factor that applies to you? Now again, treat this as a table. You have to enter. You have to see if you fit here, or if you fit here, right? So this is for tied column, meaning maybe you have a rectangular column like that, and there are a bunch of ties. Let's say we are looking at it in this view. That's a column, a bunch of ties like that, right? And again, this is my main reinforcement, and there are a bunch of ties which are going like that, and they are confining the bars that are being, maybe this is another bar being spliced, maybe this is another bar being spliced. They're confining the bars being spliced. So this splice length, you can take you can calculate it for that bar, but then you can reduce it by this factor, correct, provided you meet a certain criteria, and that criteria is what is here in this picture. So for example, this is a nice picture. I like pictures. This is a nice picture here. So let's say here is your rectangular column, has h1 dimension in this side and h1 h2 dimension on this side. So you'll have to run this check in both the direction. Let's say we are running it in this direction here. H1 is H is H1 now in this direction, and S is the spacing of the ties along normal to the screen, in and out of the screen. So you know S, you know H, and you can find this value here, right? Then in this direction, if you look at this direction, uh, the you have the area of ties is 4 times. This is 1, 2, 3, 4 times area of each bar. So you 4 times. Let's say you have um, I mean, number 9 is too much for a splice, but let's say you have a number 9, then it is um, the area of a number 9. One number 9 bar is 1, so you take, because there are 4 uh, ties, um, you multiply it with 4. So this is the effective area of those ties, and you compare that with this, correct? With this value here, and if this area is not less than that, then you can use this as your reduction factor. But you also have to run the same check in this direction. So you do the check in this direction. In this direction, let's say we're talking about this direction, your h value is nothing but the h2 spacing is the same, normal in and out of screen. But then you only have one leg and the second leg being cut. So your and again, if it is a number 9, number 9 is too much for a splice. But then if it is a number 9, so one area of one bar is 1 inch square, right? And you have 2 bars. So that is the area of that effective area of the ties. You compare that area with this ratio. If it's not, if this one is not less than that one, then you come here and take your reduction. That means you take 0.83, multiply it with the LS C value of that particular bar that you're trying to splice, right? So same story here, but then if you have a circular column and there are you have those helical ties, and there are bars that are being spliced, then here is the reduction factor that you can take, right? Then you'll have to read the section here and see if you meet that criteria, and then take the uh, and then figure out if this is an applicable value. So in short, the development length or the splice length, sorry, can be reduced by this factor or that factor, and you will have to figure out if you fall here or if you fall there, right? Again, this is a very useful diagram. It's like the, I mean, like I said, if you have a column like that, you have a P and there is a moment on the column, but the magnitude of moment is small compared to the magnitude of the axial force, the effect of the axial force. That means maybe you are falling somewhere here. Maybe this is the P value and that is your M value. So you fall in this region here. So when you fall in this region here, then you will have to, I mean, the bars will be in compression, and you can calculate your compression splice length based on that uh, section there. Um, Whereas if you based on maybe this is your P and that is your this is your M, this is your P, you fall here, then you are between those two lines there, these radial lines here. That means the actual stress in your tension steel is not compression anymore, slight tension, but then it is less than 0.5 times of Fy. So that means your area of steel provided is more than 2 times more than the area of steel required. So you can provide a class A splice if you fall in this region. So if you fall in this region, maybe your column is here. The moment the huge moment, but then the P axial load is not that much significant. So that means you will have these bars which are running like that under tension, and then you are figuring out how to calculate my LST value, right? So then you will have to um, you have to go to this table, find out the value, and you are allowed to use class B uh, ties or splices here, right? Sometimes you will be given with P and you will be given with an M value. So what you can, I mean, and you will be asked to calculate the splice length. They may be so to find out if your bars are under pure compression or if your bars are under tension, what you need to do is you open the interaction diagram, look something like this, but then the interaction diagram has on the vertical axis, let's say here, let's say this is the interaction diagram of that particular column. On the vertical axis, you have your Kn value, which is a function of your Pn, um, Fc, the strength of the concrete and the gross area. And then here on the horizontal axis, you find out your Rn value, which is a function of your Pn times your eccentricity or the moment. This is a moment. This can be replaced with M, right? Divided by your Fc dash into Ag into the depth of that column. Area Ag is the gross area. So you find out this value. I mean, to find out Kn, all that you need to do know is some geometry and property of the concrete and the axial load that is coming onto the column. So then you find out your Kn, you find out your Rn, you go to the interaction diagram, and there are similar lines on the interaction diagram there. And you figure out if you fall here, or you fall here, and then use your if you fall here, that means all your bars are under compression. You don't have to worry about tension splice length calculation. You can calculate the compression splice length from here. If you fall here, then you will have to. I mean, the bars are no more in compression. There are some bars which are in tension, and a class A splice can be used in that location. So you do your calculation based on that. If you fall here, then you will have to. That means your bars are under they have significant tension in them, and you need to provide a class B and do your splice calculation according to that section there, right? So that's about um, that's about splices. I think we started at page number 430. I think we covered a decent ground. We finished. We looked at all this, and then The end of this section, I think, is about bundle reinforcement, which is a separate discussion. All right, thank you. Let me know if you have any questions or comments. Appreciate it.